In this video, we're going to take a look at right triangle trigonometry. So we're going to start with a right triangle. A right triangle is a triangle with a 90-degree angle, and the two sides of that triangle, which meet at the 90-degree angle, are called the legs of the triangle. The side opposite the 90-degree angle is called the hypotenuse. Now, we're going to be focused on an angle of the right triangle. In particular, let's focus on angle theta here. The leg opposite angle theta, we're going to call the opposite leg. The leg that is one side of angle theta, so one side is that ray, we call the adjacent leg. So we have angle theta. The leg opposite is over here. The leg adjacent is over here. Now also, because the three angles of a triangle add up to 180 degrees, the other angle of this right triangle that's not the 90-degree angle will be complementary to theta. A lot of times people denote that as theta prime. So theta and theta prime have to add up to 90 degrees because the angles of a triangle add up to 180, and we already have one angle that's 90 degrees. So this is the layout of a right triangle. Now, when we want to do trig on the right triangle, the mnemonic we use is SOHCAHTOA. This is how sine, cosine, and tangent are defined on a right triangle. The sine of angle theta is the ratio of the length of the leg opposite of theta over the length of the hypotenuse. Cosine of theta is the length of the adjacent leg over the length of the hypotenuse. And tangent is the length of the opposite leg over the length of the adjacent leg. That's where we get this mnemonic. SOH means sine is opposite over hypotenuse. CAH means cosine is adjacent over hypotenuse. TOA means tangent is opposite over adjacent. Again, this is how sine, cosine, and tangent of an angle are defined within a right triangle. So how does this compare to the sine and cosine definitions on the unit circle? Well, on the unit circle, remember cosine of theta is the x value. Sine of theta is the y value. We can visualize that as lengths along the x-axis and length at least parallel to the y-axis. That gives us a right triangle with hypotenuse 1. If we use that right triangle with hypotenuse 1, then we get the exact same definitions. Cosine of theta is this length along the x-axis divided by 1, so it's just cosine of theta. Sine of theta is the length parallel to the y-axis divided by 1. So there we go. If we start with the right triangle, all we have to do is scale it down. As you scale it down to have hypotenuse of length 1, then everything matches up as well. So we can scale up any triangle on the unit circle to meet a right triangle of any lengths. And we can scale down a right triangle of any lengths to be similar to 1 on the unit circle. So let's go ahead and use the definitions that we've just established on a right triangle to find basic trig values of cosine theta, sine theta, and tangent of theta for this right triangle. We can see that this right triangle has hypotenuse of length 16 and theta is located in the lower left-hand corner here. The side opposite of theta is length 8. The side adjacent to theta is length 8 root 3. So here we go. SOHCAHTOA is the mnemonic that we remember. Sine of theta is opposite over hypotenuse. Now the opposite in this case is 8 over the hypotenuse of 16. That reduces to 1/2 if we want to reduce that. So sine of theta is 1/2. Cosine is adjacent over hypotenuse. Adjacent over hypotenuse would be 8 times the square root of 3 divided by 16, which is the square root of 3 over 2 when I reduce that. Tangent of theta is opposite over adjacent. That is 8 over 8 root 3, because the side opposite is 8, and here we have 8 root 3, which is the side adjacent. Again, that's going to reduce if we want to. You could rationalize the denominator there as well if you'd like. By the way, if you've watched the video on the unit circle, then those should be familiar values. If you take the cosine of angle pi over 6, you actually get root 3 over 2. The sine of pi over 6 is 1/2. Pi over 6 radians is the same thing as 30 degrees. So this angle is 30 degrees or pi over 6 radians. I mention that not because I want you to be able to find the angle at this point, but I want you to realize that, again, this is just a scaled up version of the triangle we saw on the unit circle with angle pi over 6 radians or angle 30 degrees. Now, SOHCAHTOA gives me definitions for sine, cosine, and tangent. If you want to calculate the other trig functions like secant, cosecant, and cotangent, we can just use reciprocals. Remember that secant is 1 over cosine of theta, so we just take the reciprocal of root 3 over 2, which is 2 divided by square root of 3. Cosecant is the reciprocal of sine, so we get 2 over 1 for our cosecant, so we get 2. And cotangent is the reciprocal of tangent, so that is the square root of 3. So this is why we learn a mnemonic for SOHCAHTOA, but we don't really need another tool to do secant, cosecant, and cotangent because we know how those relate to cosine, sine, and tangent. Here's another example where we have the 3 sides of a right triangle labeled. We have 60, 91, and 109 as the 3 sides of a right triangle. And here we've labeled 2 angles. We've labeled an angle alpha and an angle beta. And we want to find the cosine, sine, and tangent of alpha and the cosine, sine, and tangent of beta. Go ahead and push pause on the video and try this on your own. In a couple of seconds, I'll show you how it's done. All right, so let's go ahead and do that. Let's start with alpha here in the lower left-hand corner. Well, the side opposite of alpha is length 60. The side adjacent to alpha is length 91. And then the hypotenuse is 109. So if we're trying to find the SOHCAHTOA, a lot of times I'll start with the sine. Sometimes I'll start with the cosine. It really doesn't matter which one you start with. Cosine is adjacent over hypotenuse. That's 91 over 109. Sine is opposite over hypotenuse. The side opposite of alpha is 60 over the hypotenuse of 109. And then tangent of alpha, tangent is opposite 60 over adjacent, which is 90. So we get those values for cosine, sine, and tangent of alpha. And then as always, if I want to find secant, I would just take the reciprocal of cosine. If I want to find cosecant, I would just take the reciprocal of sine. And if I wanted to find cotangent, I would take the reciprocal of the tangent. So that is all 6 trig functions defined for angle alpha. What about for angle beta? Well, here's where we have to pay close attention. The side opposite of beta is this one, which is length 91. The side adjacent to beta is the 60. So the cosine is going to be the adjacent side to beta over the hypotenuse. That's 60 over 109. The sine of beta is going to be the opposite over the hypotenuse. That's 91 over 109. And the tangent of beta is opposite over adjacent. Again, I'm getting that from SOHCAHTOA. Tangent is opposite over adjacent. Opposite is 91, adjacent is 60. Secant is the reciprocal of cosine, so that's just 109 over 60. Cosecant is the reciprocal of sine, that's 109 over 91. And tangent is the reciprocal of cotangent, so that would be 60 over 91. I want to say 2 things here. The first is this: whenever you're dealing with these right triangles, don't use a ruler to measure the sides. While we have these pictures of right triangles, they're not going to be proportional necessarily. So the sides of these right triangle pictures will not be proportional necessarily. The other thing I wanted to point out is that since alpha and beta are the other 2 angles in this right triangle, they would have to add up to 90 degrees. So they are complementary angles. So alpha and beta are complementary angles. They add up to 90 degrees. And I want you to notice that the cosine of alpha was the same as the sine of beta. In fact, that's where we get our phrase cosine from. Whenever you think of the sine of an angle, it's opposite over hypotenuse. The cosine is the sine of the complementary angle. That's where we get the prefix co from. That's the same as cotangent. The cotangent of alpha is actually the tangent of the complementary angle. You get the same values. And similarly, cosecant of alpha is the secant of the complementary angle as well. So that prefix co comes from the fact of complementary angles. So that's where the prefix comes from. Now, in these first 2 examples, we were given all 3 sides. So we were given all 3 sides labeled in both of these examples. If we were only given 2 of the 3 sides, we could still do that, but we'd have to come up with the length of the 3rd side. The nice thing about that is that we have something called the Pythagorean theorem. And it says whenever we're dealing with a right triangle, I get this relation that says a squared plus b squared is equal to c squared, where a and b are the lengths of the legs of the right triangle, and C is the length of the hypotenuse of the right triangle. Now that we've seen this Pythagorean theorem, if we're ever given two values, we can use the Pythagorean theorem to find the third value. If I'm given A and B, I can use this to find C. But also if I were given A and C, I could use it to find B. If I was given B and C, I could use it to find A. I am not going to prove the Pythagorean theorem here and tell you why it works the way it works. That will be put in another video that will be linked in the description of this one. We're just going to use the Pythagorean theorem to do problems like example 3. We're going to find the trig values, and we'll have to find the hypotenuse of this right triangle. So here we go. Technically, if you wanted to, we could find tangent of alpha and tangent of beta because we are given the two legs. But I think what I'll do first is I'll find the hypotenuse. So we'll call 28, I'll call that length A, and I'll call 45 length B. So the Pythagorean theorem says that 28 squared plus 45 squared is equal to C squared. Now, when you type that into your calculator, 28 squared plus 45 squared is 2,809. So let me write that down. 2,809 is equal to C squared. And now I can take a square root of both sides. Now I can take the positive square root since we're talking about lengths here. A length of a hypotenuse is not going to be a negative number. So I can take the positive square root of 2,809, and lucky enough for me, it's a whole number. It is 53. That means the length of the hypotenuse is 53. Then I can go and fill out quite quickly everything for the cosine of alpha, sine of alpha, tangent of alpha, and cosine of beta, sine of beta, tangent of beta. So cosine of alpha is adjacent over hypotenuse. That's going to be 45 over 53. Once again, we just found that 53 is the length of the hypotenuse. Sine of alpha is going to be 28 over 53. And tangent of alpha is going to be opposite over adjacent. That is 28 over 45. Again, that's all according to SOHCAHTOA definitions of cosine, sine, and tangent. Let's do the same thing for beta. Beta is going to be adjacent over hypotenuse. That's 28 over 53. Sine of beta is going to be the opposite over the hypotenuse. That's 45 over 53. And then tangent of beta is 5 over 28. Once again, you see how complementary angles and the angle itself are related. Cosine of alpha is the same as sine of beta. Cosine of beta is the same as sine of alpha. Tangent of alpha and tangent of beta are reciprocals. So there you go. We can use the Pythagorean theorem to say if you know any two sides, we can find the third and then use that with SOHCAHTOA to find cosine, sine, and tangent of all these angles. In example 4, it asks us to do that same thing, except for this time, you're given one of the legs and the hypotenuse length. So you're given the length of one of the legs and the length of the hypotenuse. Use the Pythagorean theorem to find the length of the other leg, and then find cosine, sine, and tangent of both alpha and beta. Go ahead and push pause on the video and try this on your own. In a couple of seconds, I'll show you how it's done. All right, so let's do this. Length of the hypotenuse is 15 root 3. Length of a leg is 14 root 2. I'm going to call this 14 root 2 the B, and you'll see why I do that later. And the A is the leg I don't know. So we'll call the A the leg I don't know, and then we'll assume that 14 times the square root of 2 is the B. You could have switched that if you wanted to. Doesn't matter, but I'm doing it this way. 15 times the square root of 3 is the length of the hypotenuse. So what we get there is a squared plus 392 is equal to 675. Subtracting 392 from both sides gives us a squared is equal to 283. Taking a square root of both sides gives me a is equal to the square root of 283. And 283 underneath a square root is not going to be able to be simplified. We can approximate that value, but we can't simplify it any more than square root of 283. So that is the length of this leg A that I don't have. Now that I have that, now I can find the cosine of alpha. You'll notice that this right triangle I drew a little bit differently. Instead of the alpha being on the left, I put the alpha on the right. But all of the same principles hold true. Adjacent is 14 root 2. Hypotenuse is 15 times the square root of 3. So that means cosine of alpha is 14 times the square root of 2 over 15 times the square root of 3. Sine of alpha is going to be the opposite side. That's the square root of 283 that we just found, divided by the hypotenuse, which is 15 times the square root of 3. I'm going to leave it like this. Obviously, most platforms may want a rounded version of that answer. So I'm not going to deal with that, but there we go. I'm just going to leave it as the exact version. Tangent is going to be opposite over adjacent. The opposite of alpha is square root of 283. That's the one over here. Divided by the adjacent to alpha, which is 14 times the square root of 2. And then for beta, it's going to work very, very similarly. Beta, cosine of beta, again, the CAH part of SOHCAHTOA. Cosine of beta is adjacent over hypotenuse. Adjacent is square root of 283 over the hypotenuse, which is length 15 times the square root of 3. Sine is opposite of beta. Side opposite of beta is 14 root 2 divided by the hypotenuse, which again is 15 times the square root of 3. Tangent of beta is going to be opposite, which is 14 times the square root of 2 over the adjacent, which is the square root of 283. So there I found all of the values for my trig functions, cosine, sine, and tangent for both angles alpha and beta. So far, we've been calculating cosine, sine, and tangent of various angles. Now what we're going to do is we're going to do something called solving a right triangle. Solving a right triangle means finding the angles and the side lengths. And the general way we denote the sides is the following. We let alpha, beta, and gamma be our three angles of the triangle, and traditionally gamma is the 90-degree angle. Those are the first three letters of the Greek alphabet. The side opposite of alpha, we say has length A, The side opposite of beta, we say has length B, and the side opposite of gamma, we say is length C. Since the side opposite of gamma is the hypotenuse, that just means C is the hypotenuse of this right triangle. This is the standard notation. We use A and B for the legs. A is opposite of alpha, B is opposite of beta, and then the hypotenuse is C. So if we have this convention, can we find the A, the B, and the C, along with the alpha, the beta, and obviously I already know the gamma in a right triangle? In order to solve the triangle, we'll need to find the angles. It turns out if an angle is between 0 and 90 degrees, then we can use inverse trig functions to find those angles. This is how it works. If I know that sine of an angle is equal to y, and I know that that angle is between 0 and 90 degrees, then the inverse sine of the y will be equal to the angle theta. For cosine, it works exactly the same. If cosine of an angle is equal to the number x, then the inverse cosine of x will be that angle. And if the tangent of an angle is equal to a number, we'll call it z, then the inverse tangent of z will be the angle. This works really, really well when theta is between 0 and 90 degrees. If you move on later in my course, you'll see how we can amend this if angles could be other angles. So if they could be less than 0 degrees or more than 90 degrees. So let's use an example that we've already dealt with. We've already dealt with a right triangle whose legs are 60, 91, and whose hypotenuse is 109. Our goal is to find the measure of angle alpha and the measure of angle beta. Let's use the work that we've done before to find that. So we already know that cosine of alpha is 91 over 109. 91 is the adjacent side over 109, which is the hypotenuse. Obviously, the alpha and the beta have to be between 0 and 90 degrees because we already have one angle that's 90 degrees. So alpha and beta have to add up to 90, and therefore they're both between 0 and 90. So alpha is going to be the inverse cosine of 91 over 109. Now, this is something that we can plug into our calculator as long as our calculator is in the correct mode. And usually for triangles, we tend to use degrees more than we use radians. For a unit circle, we tend to use radians more than degrees. So I'm going to use degrees here. And I'm going to just type into my calculator cosine inverse of 91 over 109. And when I do that, I got 33.40 degrees, remember, as the measure of angle alpha. Now, we could have also used sine as well. And it's a good check to see that we get the right answer doing both ways. If you take the inverse sine, again, this is just a function on our calculator of 60 over 109, then you should get the exact same value. Inverse sine of 60 over 109 is equal to 33.40 degrees. Again, that's if I round to a couple of decimal places. And you could have also done this with tangent as well. You could have taken alpha and set it equal to the inverse tangent of 60 over 91. And you end up getting, once again, approximately 33.40. So now I found alpha, and I've done so in 3 different ways. Okay, I've used inverse cosine, inverse sine, and inverse tangent because I had all three of these equations. Now, there's two ways to find beta now. If I want to find beta using inverse, I can do that. I can say that beta is equal to the inverse cosine of 60 over 109. And if you do that, you're going to get a nice approximate value. So that is perfectly fine. You'll get about 56.60. I won't go through both of these other two, but they both also lead to 56.60 degrees. The other way you could have found beta after you found alpha is to realize that alpha and beta are complementary. So that means if we're talking about degrees, alpha plus beta is equal to 90 degrees. And if you know that alpha is 33.4 and we don't know beta yet, then we could have just subtracted 33.40 from 90 and gotten the 56.60 as well. So that's another way that we can do that. By the way, hopefully it's straightforward why alpha and beta are complementary. That's because alpha plus beta plus my gamma, the three angles, were 180 degrees. But we also knew that gamma, we're using a right triangle, so gamma was 90 degrees. So subtracting 90 degrees from both sides, we get alpha and beta have to add up to 90, so they're complementary. So we can use inverse cosine, inverse sine, or inverse tangent to find angle alpha if I know the side opposite and the side adjacent, or the side opposite and the hypotenuse, or the side adjacent and the hypotenuse. Whichever ratio I know, I can just use the appropriate inverse cosine, inverse sine, or inverse tangent to find alpha. And then I can do the same thing with beta, or I can just realize alpha and beta are complementary angles. We won't always be given the three sides. So we won't always be given the three sides, but you could imagine from what we did earlier, if you were given two sides, you could find the third using the Pythagorean theorem, and then use trig inverses to find alpha and beta. Or if I knew alpha and b, I might be able to use that to find the hypotenuse using SOHCAHTOA, and then the Pythagorean theorem would give me the a, and so on and so forth. In other words, we have a lot of tools that we've developed in order to solve right triangles. I can use any of the relations from SOHCAHTOA, that is, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. I can use the inverse trig functions. I can use the Pythagorean theorem, and I can use the fact that the angles of the triangle add up to 180, making alpha and beta complementary when I have gamma as a 90-degree angle. And in general, you can always just say angles of the triangle add up to 180 degrees. So with those tools that we have now, we can solve right triangles if we're given a couple of pieces of information. Let's try this example. We're only going to be given two pieces of information. The first is that the length of A is 18. The second is that the angle measurement of alpha is 30 degrees. All right, so let's go ahead and do this one. Solving the right triangle means that I come up with every single angle and with every single side length. So I need to find alpha, beta, and gamma, and I also need to find A, B, and C. And we're given this information. We're given that A is equal to 18 and alpha is 30 degrees. So we're given A is 18 and alpha is 30 degrees. So we're given that information and we need to find all of the rest. Now, the other piece of information is I'm using a right triangle where gamma is 90 degrees. So we have alpha, A, and gamma that are given to us. Now what I would do is since I know alpha, I'm going to use some rule for SOHCAHTOA. Notice that I am given the length of A, which is the side opposite of alpha. So that means the sine of alpha is A over C because A is the side opposite of alpha and C is the hypotenuse of this right triangle. I know that alpha is 30 degrees and I know that A is 18. So I can solve this equation for C. Now sine of 30 degrees is 1/2. It should be fairly obvious that C has to be double 18. It has to be 36. So now I know that the length of the hypotenuse is 36. So C is equal to 36. If I wanted to, I can actually use the same thought process with tangent is opposite over adjacent. And for alpha, the adjacent side would be B, the opposite side would be A. So you could use the TOA part to find your B, just like I use the SOH part to find my C. But another way you could have done this is you could have found B using the Pythagorean theorem. The Pythagorean theorem says A squared plus B squared is equal to C squared on a right triangle. A here in this case is 18. B is the unknown that I don't know. C I now know is 36. 18 squared is equal to 324. 36 squared is 1,296. If I subtract 324 from both sides, I get B squared is equal to 972. By the way, if I take a square root of that, I end up with a B value simplified, which is the square root of 972. Again, I'll simplify this real quick. That's the square root of 324 times 3. Square root of 324 is 18, so it's 18 times the square root of 3. So that's the B value. Now, this is an exact value. Sometimes you might be asked to write an approximate answer. But that's our value for B, 18 times the square root of 3. Now, there's lots of different ways to find beta, but probably the easiest way to find beta is once we've established alpha, alpha is 30 degrees, so beta is going to have to be 60 degrees because they have to add up to 90. 90 because the three angles of the triangle add up to 180. That is 180 degrees. So if I know that alpha is 30, I don't know beta yet, but I know gamma is 90. Subtracting 30 and 90 from both sides gives me a beta, which is 60 degrees. And now I have all of the information on this right triangle. I know all three angles, and I know all three side lengths. Now, not every time are we going to have angles that are nice 30 degrees and 60-degree angles. Here's an example. This is example 7, where it's asking us to solve a right triangle. And it gives us that the angle beta is 38 degrees and the length of the hypotenuse is 27.3. I want you to push pause on the video, try this on your own. In a couple of seconds, I will show you how it's done on the video. All right, so let's go ahead and do this one. We want to solve the right triangle. We're given beta is 38 degrees, and we're given that C is 27.3. I know that this picture is just for reference and that the sides and angles are not proportional to the actual picture. But what we do know is that we're going to say gamma is always our 90-degree angle. And we can either find the A, the B, or the alpha next. In the previous problem, I started out finding the A's and the B's. I started finding the side lengths first. In this one, let me find this missing angle. So we have alpha plus beta plus gamma has to add up to 180. We don't know the alpha yet, but we do know that the beta is 38, and we do know that the gamma is 90. We would have to subtract 38 from both sides and subtract 90 from both sides to solve for alpha. And it would say that alpha, our angle alpha, is equal to 52 degrees. So alpha is 52 degrees. Now I want to find A or B, and I'm given the length of C. I'm given the length of the hypotenuse. So now I'm going to use one of my SOHCAHTOA relationships. So we can use the SOHCAHTOA relationships with alpha. We can use the SOHCAHTOA relationships with beta. But we have to use one of the ones which involves the hypotenuse. I can't use tangent because tangent is going to be opposite over adjacent. Depending on which angle we use, that's either going to be B over A or A over B. Both the A and the B are unknown. So I have to use one of either the sine relationships or the cosine relationships. Let's use the sine of beta relationship since I'm given beta. Sine of beta is opposite over hypotenuse. In this case, the side length opposite of beta is B. The hypotenuse is C, obviously. So sine of 38 degrees is equal to the B over, I know C is 27.3. Now, if I wanted to find the exact value for B, I just need to multiply both sides by 27.3. 27.3 times the sine of 38 is the exact value for B. But more likely, it'll probably ask you for an approximate value. And when you type that into a calculator, making sure you're in degree mode, you'd get about 16.81. So we get a B value that's about 16.81. I should put approximately there. If I want to find the A value, I can do something very similar. I can use the cosine of beta relationship. Let's go ahead and do that. For this relationship, we'd have cosine of beta is equal to adjacent over hypotenuse. If we're talking about beta, the side adjacent to beta is A. The hypotenuse is C. So I could do the exact same thing there, except with cosine, obviously. So we have cosine of 38 is equal to A over 27.3. The exact value for A is going to be 27.3 times the cosine of 38. But again, most of the time, you're probably going to want an approximate value for that, and that's about 21.51. So there we go. Now we have A, B, and C, and we have alpha, beta, gamma. One little note on this, after I found the B value, and I already knew the C was 27.3, I could have also used the Pythagorean theorem to get A. And if we would have done it that way, we would have gotten something that is very, very close. If we would have rounded it to 2 decimal places, you would have gotten the exact same value, 21.51. But if you would have rounded this one further, you get 21.5127, whereas this one gives you 21.5108. The reason for that discrepancy is we used a 16.81. That's already a rounded value. If I use the exact value of 27.3 times sine of 38, then this would have also came out to 21.5127. So you might get a slight discrepancy based on how you solve if you are plugging in already rounded values into the formulas you're using. In any case, we just saw how to solve this right triangle. For the last example, it asks us to solve a right triangle, knowing that one of the leg lengths is 42.9 and the hypotenuse is 51.6. Go ahead and push pause on the video and try this one on your own as well. In a couple of seconds, I'll show you how it's done. All right, in this case, we're given the right triangle. We're given that B is 42.9, C is 51.6. Gamma is always going to be 90 degrees on a right triangle. Now, the first thing I have to do is figure out which thing I want to find first. Do I want to find my A? Do I want to find my alpha? Do I want to find my beta? Really doesn't matter. If I want to find A first, then I can use the Pythagorean theorem. A squared plus, in this case, 42.9 squared is equal to 51.6 squared. If I do the arithmetic on that, A squared plus 1840.41 is equal to 2662.56. Subtracting 1840.41 from both sides gives me A squared is equal to 822.15. If I want an exact value, A is the square root of 822.15. Usually an approximate value is just fine. So approximately 28.67 is the value for A. So that's what we get as our value of A. Again, remember that is a rounded number. So that's how I could find the value for A if I wanted to do that first. Now, we could have also found alpha or beta first if we would have liked, using the relationships of SOHCAHTOA. Here's what I'll do. Let's say we know B and we also know C. So we know the B and the C. If I want to find alpha, well, cosine of alpha is going to be B over C. So cosine of alpha is equal to B over C. And I already know that B is 42.9 and C is 51.6. So I know cosine of alpha is equal to 42.9 divided by 51.6. And that means my alpha, since the alpha is between 0 and 90 degrees, is going to be equal to the inverse cosine of 42.9 over 51.6. This is something I can type into my calculator. As long as my calculator is in degree mode, it'll give me an alpha in degrees. We could say the approximate answer is 33.76. So alpha is about 33.76 degrees. If I wanted to find beta, there's a couple of ways I could do it. I could use the fact that sine of beta is b over c and do the exact same calculations here. Or probably what would be the easier way to find beta now is to realize that that is the only angle that I haven't found. So that means alpha and beta and gamma have to add up to 180. I know that alpha is 33.76 approximately. I know that gamma is 90. So I can solve this for beta. 180 minus 90 minus 33.76 is going to give me a 56.24 as my angle beta. Since alpha was a rounded value, beta would also be a rounded value. And I have all three side lengths. So now we've solved right triangles. We've solved right triangles in the case where we had two sides of a right triangle. We had solved a right triangle in the case where we had one side and one angle. Here we had the hypotenuse and an angle. In question 6 or example 6, we had a side of a leg and an angle. So if I have an angle other than the 90-degree angle, along with a side length, I can solve the right triangle. If I have two sides, I can solve the right triangle. There are scenarios in which it's impossible to solve the right triangle, and that's where I'm only given like one piece of information. If you're only given one side of a right triangle, then you can't find the other two sides just based off of one. And I can't find the angles based off of just one side. So if you're given one side, you wouldn't know how to solve the right triangle. And similarly, if you're given just one angle and you're not given any side lengths, then you can't solve the right triangle either because there's lots of similar triangles. The key tool that we had to use in all of these examples was SOHCAHTOA. We had SOHCAHTOA. We also had the other tools. Remember, SOHCAHTOA means sine of theta is opposite over hypotenuse, cosine of theta is adjacent over hypotenuse, and tangent of theta is opposite over adjacent. Knowing SOHCAHTOA and then being able to use the inverse trig functions and then being able to utilize the Pythagorean theorem and utilize the fact that the three angles of a triangle add up to 180 degrees, we can solve the right triangle. And so that concludes this video on right triangle trigonometry.